Assalamualaikum warahmatullahi wabarakatuh. Nama saya Nur Naki Hakimi bin Shuaib, CE 250064.
Assalamualaikum warahmatullahi wabarakatuh. My name is Anwar Labid bin Anam Rahman. My metric number CE 250054.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq bin Kamaluddin. My number metric is CE 250011.
Hi, Assalamualaikum. My name is Muhammad Hafizul bin A. Aziz. Metric number CE 250007.
Assalamualaikum. My name is Muhammad Adafir Daus bin Jasmi and my metric number is CE 250033.
Calculus of a multiple variable is an important mathematical subject that extends the concept of calculus to function involving the more than one variables. One of the important topic in this subject is a double integral. Polar coordinate represent point in terms of radius and angle, making them very useful for areas with circular or symmetrical boundaries.
Hi everyone, we're solving this double integral doing this Cartesian coordinate mean dealing with messy square root. So we are going to pivot and solve it using polar coordinate instead. Look at the boundary y equal to plus minus square root 9 minus x square. If we square both sides and rearrange, we get x square plus y square equal to 3 square. As the graph shows, our region is a full circle center at the origin with a radius of 3. This gives us our new polar limit. The radius r goes to from 0 to 3. The angle theta goes from 0 to 2 pi to sweep the whole circle. Next, we convert the component. Substitute y equal to r sin theta. Swap dy dx for the polar area element r dr d theta. Our new simplified integral becomes the double integral of 4r minus r square sin theta dr d theta. We integrate with respect to r first, plug in our bound from 0 to 3, get 18 minus 9 sin theta. We finally integrate with respect to theta from 0 to 2 pi. This sign term completely cancel out over a full rotation, leaving us with just 18 multiplied by 2 pi. Our final answer is 36 pi. Thank you.
Hey everyone, my name is Muhammad Hafizul bin A. Aziz. Matrix number CE 250007. Today we are going to write a MATLAB script to calculate a double integral in polar coordinates and visualize its region of integration. First, let's define our symbolic variables r and theta. Next, we define our polar integrand function f underscore polar, which equals 4 minus r multiplies sine theta multiply r. To find the exact answer, we use MATLAB's built-in integer function, nesting them to integrate with respect to r from 0 to 3 and theta from 0 to 2 pi. With the calculation set up, let's use fprintf to display our exact calculated value cleanly in the command window. Now, let's move on to generating the graph. To draw the boundary circle, we define a parameter t ranging from 0 to 2 pi with 200 points using linspace. Since our radius is 3, our parametric equation for the circle x equal to 3 cos t and y equal to 3 sin t. To visualize this region effectively, we open a new figure and use the fill function. This allows us to color the inside of the circle blue with a subtle transparency setting, while simultaneously drawing a solid blue outline. We call hold on so we can overlay more details. Let's add clear distinct x and y axis through the center using X line and Y line with a thin dark line profile. Finally, let's polish our graph. We apply axis equal to ensure the circle doesn't look stretched and turn the grid on. We will set custom limits on both axes from -4 to 4 and add our axis labels. For the title, we dynamically embed our calculated result into the text header using sprintf. Let's hit run. As you can see in the command window, our exact answer is 36 pi and the generated figure beautifully highlights our circular region of integration with the exact calculation displayed right in the title. Thanks for watching.
Hello everyone, today I will explain question 2e. Based on the original limits, y goes from 0 to the square root of 4 minus x squared and x goes from -2 to 2. This forms a upper semicircle regions with a radius of r equals 2. Now, we convert this to polar coordinate. The limit for r are from 0 to 2. The limit for theta are from 0 to pi. Next, we substitute the variable. S equals r cos theta. The square root component equals r. And dy dx becomes r dr d theta. After simplifying, the new integral is r cos theta dr d theta from 0 to 2 and 0 to pi. For the calculation, first integrate with respect to r, which give r square over 2 times cos theta. Apply the limits from 0 to 2 and we got to cos theta. Second, integrate to cos theta with respect to theta, which give to sin theta. Finally, apply the limits pi and 0 to sin pi minus to sin 0 equals 0. So the final answer is 0. Thank you.
We begin by declaring r and theta as symbolic variable using the syms command. This instructs MATLAB to treat them as mathematical variable for exact calculus operation rather than numerical matrix. We use nest int function to evaluate the double integral. The inner integral evaluates the radius r from 0 to 2 and the outer integrals with the angle theta from 0 to pi, the upper half plane. Finally, we print the exact analytical result directly to command window. To plot the region of integration, we define a vector x using linspace spanning from -2 to 2 divide into 200 distinct points for a smooth curve. We compute the corresponding y coordinate using the algebraic equation for the upper half of a circle y equal to square root of 4 minus x squared. This perfectly matches our integration boundaries where the maximum radius r equal to 2. The figure command open up the dedicated window to draw our upcoming visualization. We use the fill function to both shade the region and outline its boundary, passing our x and y coordinate create a closed polygon from the curve down to the x-axis. We color it blue, set a phase alpha of 0.2 to make it transparent so the grid remain visible, and create a solid 2-point thick blue border using edge color and line width. We run hold on to prevent MATLAB from wiping the shader region when they add more line. We also enforce as is equal to that one unit of the x-axis physically match one unit on the y-axis. This guarantee our semicircle look like a perfect circle and is not distorted into an oval. We toggle the background grid on add pad our view window using X limb and Y limb from -3 to 3 horizontally and -1 to 3 vertically to give the shade some breathing room. For the labeling, standard text label are added to our X for clarity. Lastly, we use sprintf to generate a multiple line title. It automatically inject our calculate variable answer value straight onto the top of the plot. We then close the plotting session with hold off. Then we hit button run. There are a few error, but we be able to fix that. Everything is aligned flawlessly now. The calculus bound perfectly detect the visual simulation.
Hello everyone, my name is Muhammad Hafizul bin Aziz, matrix number 250007. Today I will be presenting the calculation for question F. So, our original problem is the integral from 0 to 2 with respect to x and 0 to x with respect to y of the function y dy dx. First, let's identify the region of integration. Looking at the limits, y range from 0 to the line y equal to x and x goes from 0 to 2. This forms a right-angled triangle. To convert this to polar coordinates, we find the angular bound theta from the line y equal x, which gives us theta equal pi over 4. For the radial bound r, the vertical boundary is x equal to, since x equal r cos theta, substituting this gives r equal 2 over cos theta, or simply r equal 2 secant theta. Therefore, r range from 0 to 2 secant theta. Okay. Next, we convert the integrand and the differential area element. In polar coordinates, y equal r sin theta and dy dx equal r dr d theta. Substituting this into our new limits, our integral becomes the double integral from 0 to pi over 4 and 0 to 2 secant theta of r square sin theta dr d theta. Now, we perform the inner integration with respect to r. Integrating r square gives r power of 3 over 3. Evaluating this from 0 to 2 secant theta, we substitute the upper limit to get 2 secant theta power of 3 over 3 sin theta. Simplifying this expression allows us to pull out the constant, leaving us with 8 over 3 times the integral from 0 to pi over 4 of secant power of 3 theta sin theta d theta. Okay. To solve the outer integral, we rewrite secant power of 3 theta sin theta as sin theta over cos power of 3 theta, which can be simplified neatly into tangent theta secant squared theta. We can easily solve this using u substitution. Let u equal tangent theta, meaning du equals secant power of 2 theta d theta. changing our integration limits based on u theta equal to 0 becomes u equal 0 and theta equal pi over 4 becomes u equal 1. Our integral simplifies beautifully to 8 over 3 times the definite integral from 0 to 1 of u du. Integrating u gives u power of 2 over 2. Evaluating this from 0 to 1 yields 1 over 2. Finally, multiplying 8 over 3 by 1 over 2 gives us our final answer of 4 over 3. That concludes my presentation. Thank you for watching.
Okay, first of all, we need to put SYM SR theta because we use polar coordinate. Then, first step is calculate and display the exact answer. We put function polar equals to the equation that has been given. Then we put quotes answer underscore value equals to integer function polar r theta 2 seconds theta and theta 0 pi over 4. Then we use f print f. We write the exact calculate answer is the value that will be given at the output waveform and output command prompt. Then second step is a generic graph. We used to get the graph double integral. Firstly, we put the x value, which is a 0, 2, and 2, and y value is a 0, 0, 2. Then we figure out for the step 3, we use a triangular region and draw the outline in one step to make a draw into the drawing and graph. Okay, then we fill out the codes to get the color codes to make it have a line inside the graph. Then fourth step is draw x and y axis. So we put coding x line. Then we put x line, so x line codes, which is 0k line width 1.5, and y line is a same code but just need to change the x line to the y line. Then fifth steps is format the graph, which is x is equal grid on. X lim is a limitation, so we put a limitation -1 to 3, and y limitation is a -1, 3. Then we put x label to get the x axis, and y label to get y axis. Then we write the codes to the title sprint f region of integration for a problem f calculated answer. After all error has been repaired and has been correctly, we can run it and the value is 4 over 3, and we can see there's a output triangular shape.
In conclusion, this project successfully demonstrated the application of polar coordinate transformation in solving double integrals. Comparisons between manual solution and MATLAB simulation show that both methods produce consistent answer, proving the accuracy of the calculations and the reliability of the software. Through this project, the group gained a better understanding of the concept of multivariable calculus, particularly the use of coordinate transformation in simplifying complex integration problems. That's all from me.